In this study, we delve into the fascinating world of nutrition and its impact on weight gain, using our furry friends rats as our subjects. Our mission is to compare the effectiveness of 3 different diets in influencing weight gain in rats over a month. To achieve this, we'll be employing a statistical tool known as Duncan's multiple range test. This test allows us to determine if there are significant differences in weight gain among the groups of rats assigned to each diet. By the end of this analysis, we aim to answer the pressing question: which diet, if any, leads to the most substantial weight gain in our rat population? Let's embark on this scientific journey to uncover the dietary secrets behind rat weight gain. To begin our investigation, we randomly divided a group of rats into 3 groups, each receiving a different diet. Diet A is a standard laboratory rat chow, Diet B is a high-protein diet, and Diet C is a high-fat diet. We meticulously tracked the weight gain of each rat over the course of a month. The data collected represents the weight gain in grams for each rat within its respective diet group. Diet A, Diet B, Diet C. 10, 12, 15, 11, 14, 16, 12, 13, 18, 13, 15, 17, 14, 16, 19. This table provides a snapshot of the weight gain observed in each group. Now, let's delve deeper into analyzing this data to uncover any significant differences between the diets. To compare the effectiveness of the 3 diets, we first need to determine the average weight gain for each diet group. This is called the mean. We calculate the mean by summing up the weight gain of all rats within a group and dividing by the number of rats in that group. 10 plus 11 plus 12 plus 13 plus 14, 5 equals sign, 12 plus 14 plus 13 plus 15 plus 16, 5 equals sign, 15 plus 16 plus 18 plus 17 plus 19, 5 equals sign. These means provide a preliminary indication of the average weight gain associated with each diet. Diet C, the high-fat diet, appears to be linked to the highest average weight gain, followed by Diet B, high protein, and then Diet A, standard. Now that we have calculated the mean weight gain for each diet group, let's determine the overall mean weight gain for all the rats in the experiment. This gives us a central value to compare each diet group against. To calculate the overall mean, we sum up the weight gain of all the rats, regardless of their diet, and divide by the total number of rats. 10 plus 11 plus 12 plus 17 plus 19, 15 equals sign. Interestingly, the overall mean weight gain of 14 grams is the same as the mean weight gain for Diet B. This suggests that Diet B's effect on weight gain might be similar to the average effect of all diets combined. Section 5. Sum of squares measuring variation in weight gain. To determine if the differences in mean weight gain between the diets are statistically significant, we need to quantify the variation in weight gain. We do this using a measure called the sum of squares. There are 3 types of sum of squares we need to calculate. First, the total sum of squares, or SST. This represents the total variation in weight gain among all the rats, regardless of their diet. We calculate it by taking the difference between each rat's weight gain and the overall mean weight gain, squaring those differences and adding them all up. Second, the sum of squares between groups, or SSB. This measures the variation in weight gain between the 3 diet groups. It is calculated by taking the difference between each group mean and the overall mean, squaring the differences, multiplying each squared difference by the number of rats in that group, and adding those values for all groups. And finally, the sum of squares within groups, or SSW. This measures the variation in weight gain within each diet group. It is calculated by taking the difference between each rat's weight gain and its group mean, squaring those differences and adding them up for all rats. These sums of squares are essential for calculating the F statistic, which helps us determine the significance of the differences between the diets. Section 6. Degrees of freedom, understanding our data's flexibility. Degrees of freedom represent the number of independent pieces of information that are free to vary in our analysis. Understanding degrees of freedom is crucial for interpreting the results of statistical tests. Degrees of freedom between groups, or DFB, refers to the number of diet groups minus 1. In our case, we have 3 diet groups, so DFB equals 3 minus 1, which is 2. Degrees of freedom within groups, or DFW, represents the total number of rats minus the number of diet groups. In our case, DFW equals 15 minus 3, which gives us 12. Total degrees of freedom, or DFT, is the total number of rats minus 1. In our case, DFT equals 15 minus 1, which is 14. These degrees of freedom values will be used in calculating the F statistic and interpreting the results of Duncan's multiple range test. Section 7. Mean squares and F statistic assessing differences between diets. Mean squares are calculated by dividing the sum of squares by its corresponding degrees of freedom. Mean square between groups, MSB, is calculated as SSB divided by DFB. Mean square within groups, MSW, is calculated as SSW divided by DFW. The F statistic is a ratio of the variation between groups to the variation within groups. It helps determine if the differences in mean weight gain between the diets are statistically significant. The F statistic is calculated as MSB divided by MSW. A larger F statistic indicates that the variation between the groups is larger compared to the variation within the groups, suggesting that the diets may have different effects on weight gain. Section 8. Duncan's test ranking diets based on weight gain. Duncan's multiple range test is a post hoc test used to determine which specific diet groups are significantly different from each other after a significant F statistic is obtained. This test ranks the means and compares the differences between them with a critical value. If the difference between two means is greater than the critical value, then the two groups are considered significantly different. We use a table of critical values based on the degrees of freedom and desired significance level, usually 0.05. Section 9. Comparing and contrasting which diet reigns supreme. By performing Duncan's multiple range test, we can determine which diets result in statistically significant differences in weight gain. The test ranks the means and compares the differences between them to a critical value. We can then draw conclusions about which diets lead to the highest and lowest weight gain. For example, if the test shows that diet C, high fat, leads to significantly higher weight gain than both diet A, standard, and diet B, high protein, and there's no significant difference between diet A and diet B, we can conclude that diet C has the most substantial impact on weight gain. Section 10. Conclusion. Unveiling the diet with the biggest impact. Through this detailed exploration of Duncan's multiple range test, we have gained valuable insights into the relationship between diet and weight gain in rats. By calculating group means, overall mean, sum of squares, degrees of freedom, mean squares, and the F statistic, we laid the groundwork for comparing the effects of 3 different diets. Duncan's test allowed us to pinpoint the specific dietary groups that differed significantly from each other. Ultimately, this analysis allows us to determine which diet had the most significant impact on weight gain, providing valuable information for understanding the nutritional needs of our rodent companions and potentially extrapolating those findings to broader dietary contexts.